We challenge topic number 2, air muscle.
Number 2, hold on the set on the chair.
We set the challenge.
Okay, accept.
Air muscle.
Please find the name of the presenter on the board.
不好意思，这应该是一个不知道哪一个黑色底的图片，不知道。
你在哪里找到？
那个。
那你做你要问问他那女生是不是？
这样的。可以过一。
或者是他们中间 reviewer， 中间啊有，
所以先放
那个。
Reporter, you may start when you are ready.
Good afternoon. I'm the reporter of Aztec Banana, and my topic is air muscle. So these are the table of contents. First, introduction, theoretical model, conclusion, experiment, and experimental setup. This is the problem statement. The balloon is placed inside a cylindrical net, sometimes used to wrap garlic, and inflated. The web will expand and shorten, studying the properties of this muscle. So these are the parameters that will be used later. R stands for radius of balloon, and length is length of cylindrical net. This is star theory. The relationship between balloon elasticity, internal pressure, initial radius, and final radius. according to the formula of ideal air, we can get this. And this is the volume of the balloon. And the change of the pressure equals this. And Y stands for Gauss modulus, T stands for thickness of balloon, and it equals the inner pressure minus the outer pressure. Change in length and Y. L as the shortened length equals this. And this L is the original length of the flap, which is this. And if we divide this from R, we will get this. So this is the force versus elongation relationship. Because the expand of the balloon is not limited, so the volume won't change, which we can get this. And the pressure that was given from the flap will be the force divided the contact area, and it is nearly equal to this. The inner pressure equals the outer pressure plus the pressure of T and the pressure of flap. And pressure of T will be this, as mentioned before. This is the force versus elongation relationship. Upper. From this formula, we can get this. This is the line of the balloon, and from calculation we can get this, which can be used later in the calculating. So this is the change of the length, and we know the amount of B, so it will be like this. Experiment setup. This is how we set up the experiment. First, we put the balloon in a cylindrical net, and we place the wet down the left. And this is a spring balance and a storm cowl. So this is a device that we press the air into the balloon. And this is the valve you can turn on or turn off it to change the volume you pressed into the balloon. And this is where the balloon pressed. This is the needle, and each of them is 60 ml. Experiment. So this is the experiment process. The orange one is calculated by the formula, and it's calculated by the formula, and the blue one is from the experiment. As you can see, the relationship between the radius and the needle is a positive correlation. So this is the overview chat of all the data, and it is a 30 chat. This is the relationship between the force and the length. As you can see, nearly all the lines are stable except the one with zero pressure. And this is calculated by theory, and this is a real experiment. So it matches nearly. Experiment process. This is the chart with the force and the width of the balloon, and nearly each of the lines are stable, and so does the line with experiment. This is a relationship between the needle and the width of the balloon. It has a positive correlation, and the more we the wider the balloon expands. So that's the experiment. So this is the relationship between the needles and the length of the cylindrical. If we add more needles to it, the cylindrical, the length of the cylindrical will shrink more. But there's an exception, is there's an offset line when the needle when the flash weight is 20 kilograms. So this is capturing the needles and the width of it, and it is also positive reflection, and so that's the experiment. Conclusion. Increasing inflation expands radius and shortens length. Adding load further shortens out, showing match constant effects. So the theoretical analysis versus the radius. The internal pressure and the volume relation will be this. The inner press goes the outer press plus the press of T and the press of F. The effective tension will be this, as mentioned before, and the elastic tension affects radius. So the constraint radius Y will be equilibrium relation will be this, and external force affect deformation. So the length, the geometric deformation relation will be this, and the length variation will be this. Matching experimental observations. So this is the end of our report.
Question of the opponent.
So first of all, I would like to ask you the variables you measured. So the only independent variable in your experiment is the radius of the balloon. Is that right?
Can you repeat it again?
Could you define the independent variables in your experiment?
Oh, and first is the needle. The additional pressure to the balloon, and another is the flash weight.
So you added weight. You measured the liters.
The independent variable is the weight and the needles of the press.
The what?
The pressure.
The pressure.
Yeah.
So you change the pressure and the weight.
Yeah.
Okay. Did you keep the cross-sectional area of the balloon uniform? So is the balloon a sphere at all times?
Expand at all times.
A sphere.
Sphere. What do you mean?
Like does it look like a circle? A sphere.
Yes, near the circle.
Okay. Does your system always reach equilibrium? So for your measurements, was it always measured at equilibrium?
Yeah, no.
Did you account for elastic tension, like how it affects the radius? Because you mentioned it in your conclusion that you don't have any other type of system.
Yeah, we don't.
So, okay, thank you.
So you have 3 minutes to prepare your report.
So we can also
Morgan Tsai from No Niners, and I'm going to be the opponent for topic number 2, air muscle. Let's first look at the problem statement. So the problem statement is to place a balloon inside a net similar to one that you were back garlic and inflate it. The net will expand and investigate the properties with relevant parameters of such a muscle. So the ideal structure of the investigation is first to put the balloon inside a net. Then you add pressure using a syringe, similar to what the reporter did, and then measure the width, so the change in the balloon's width with respect to the pressure added. Then after that, put it in water and do the same thing. This time, measure the displacement of the water to get the volume inside the balloon that you added into the system. So this is the opponent's structure of solving the problem. Oh, the reporter. So the reporter modeled the balloon expansion and force applied. First, they put a sphere inside a net, a vertical one, and then they compared the qualities. So the parameters they measured were the pressure, which is the volume and pressure, which is given by the syringe. And then they also measured the force versus the length, and then the number of needles to the width. So pros and cons of the reporter. So the pros is that the reporter had a clear paced voice and a nice experimental setup with relevant diagrams. But a con is that there's an unclear comparison of the theory to the experiment, and they use needles instead of volume for certain comparisons, which could account for some deviation. And then the relationships looked for correlation instead of a relationship. So there's more correlation was shown instead of measuring the relationship of their parameters. And then lastly, the reporter, even though their pacing had a nice clear pacing, their slides were not sufficient enough to reach the timing requirements. So I would like to invite the reporter up for some discussion. First, can we talk about your parameters? So the weight that you attach to the balloon. As you attach weight to the balloon, this would change the shape of the balloon for causing it to not be a sphere, as you said when I asked you a question about it. So do you have any justifications for if it doesn't act as a sphere, your calculations were meant for a sphere-like structure?
So same the balloon as a circle shape because it's more easy to calculate. If you really use what the real shape is, it's hard to calculate.
So you didn't account for, as you put weight on this balloon, it could cause the shape of the balloon to differ. Therefore, it may not be an ideal sphere calculation. So I have my contributions are to use a cone sphere model because as the weight is put onto the balloon, it pulls it down, therefore creating a cone-like structure for the ends of the balloon, and the middle part would act more like a sphere.
But I think the balloon will not matches the real shape of the balloon. I think circle matches this more.
Okay. Next, for the pressure, you mentioned how, did you use needles or?
I think you mistake my meaning. Needles there's a volume in the needle, so the needle means a volume of needle. Like how to explain? Like you grab.
Okay, so we continue on. So I think you meant by syringe, you have a syringe that puts pressure air into the system, right? So because you use a syringe, wouldn't there be air inside of the syringe or the tube leading up to the balloon that you don't account for? Therefore, not all the air that's being pushed out that goes into the balloon for it to expand.
Yeah, it may be, but it's minor.
Okay.
It's just minor.
Also, the elasticity of the balloon. So you did mention in your concluding slides how the elasticity affects your relevant parameters. However, I think the elasticity contributes more than just a one-sentence conclusion or any measurement that you could have done, such as changing the balloon or measuring its elasticity with respect to different balloon times. Do you have your opinions on this matter?
I think that the elastic potential really matters, but we can analyze it. So I think I will predict if it is a conservation of energy. I think we can calculate the elastic potential loss of energy because the velocity energy doesn't change, so we can calculate.
Could you explain as to the velocity of the energy for what?
Because it is stable first, and there's no velocity after the experiment, so it doesn't change the energy.
I disagree because as you pump air in, of course the balloon would change, therefore the velocity would also be affected.
But it's the velocity is there's no velocity.
Okay, wait, can we continue on? So for conservation of material, did you account for this in your experiment?
I don't change the material.
No, conservation of material means as the balloon is expanded, there is also force pressure from the balloon pressing in onto the system, not the different material. So like your set of material has its own conservation material acting against it.
I think I mentioned it. There's a force on the contact of the surface between the cylindrical and the balloon.
And did you account for the conservation of material?
Yes, that's that in the theoretical model.
But did you do anything with it for your actual model, or was it only slightly mentioned in your theory?
Just in the theoretical model.
Okay. Also, you mentioned how you use the gas law, right?
Yeah.
Okay, but the ideal gas law does not actually, it's not as ideal as mentioned. Did you account for any deviations? Because in your presentation you didn't account for the errors or here's ideal gas law.
We assume the ideal gas law because it is, even though it's not ideal, but it is a theoretical model, so it is just an assumption.
Did you account for how as you add more pressure and air into the system, there is more molecules added, therefore it would speed up the molecules inside of your balloon? So you didn't account for this.
Yeah.
and this may also affect your ideal gas law calculations. Do you agree?
Yeah.
Okay. And we use pressure as force over area, right? But as the balloon changes and more weight is added, the cross-sectional area therefore also changes. Did you change the area based off of this?
What do you mean?
Because the pressure is force over area, right? And the area is the cross-sectional area of your balloon. As the balloon changes its area, and therefore the middle part, as when you said, when weight is added, the balloon's for the width decreases.
Yes.
Did you account for these?
So you mean that the area was it's changeable? I think it's just a minor of changeable. So
Okay, so you're saying that pressure is force over area, and as you add weight, because the balloon changes in its shape, you're not accounting for the area that it changes shape.
yeah.
Okay. I have a suggestion for you is that because pressure, using this formula, the change in pressure would actually be able to be calculated through the change in area because your initial balloon, could I take you? Okay. So, initially your balloon will look like this, right? And then this is the vent. Am I similar to this? Okay. So as you put pressure in, this system becomes, the balloon would be greater in width. Is that correct? Okay. But you did not account for, this is the cross-sectional area where pressure equals force over area, right? As the area of this cross-section changed, you didn't account for this area. Okay. So therefore your change in pressure would not be.
This is why it doesn't go to some it's just in the theoretical model. So it's just
And could you explain them? What did you use to account for this?
like
So you put this in your theoretical model, but you don't use it. Then could you reiterate what you did to account for this if not the area?
that's not adding the area.
Yes, and you did use the area.
If we didn't use the area, then we use pressure. This is our original objection to the
Could you explain that?
like this is like a solid added force to the balloon.
Yes.
So we need areas to be
Yes.
So
So you assume that the area of the cross-sectional area as you add pressure into the balloon doesn't change.
it's hard to
A suggestion for calculating the area would therefore be to measure the initial cross-sectional area, which would therefore be the width of this to this, using the radius, because that would be the cross-sectional area, right? And then measure the final one as pressure is added in. But you said the area does not change in your experiment. Then what?
it might change, but in the theoretical,
Then what did you account for this change? Because if you're saying the area is kept a constant, what changed? Since area is the forefront of the change in pressure. Then let's go back to the problem statement. It's as the balloon expands and contracts, how does the relevant parameters affect it? So therefore, as the balloon expands and contracts, your relevant parameters is the force on the balloon. we go back. So as the pressure in here is therefore expanded, take into account for that pressure of how there's more contact with the balloon as this is expanded. What's the next?
Like if we add that, as the balloon might extend it.
Okay, time's up. Opponent, please summarize the discussion.
Okay, so the summary of the discussion is, first of all, we talked about the volume approximation. So we disagreed on the balloon being a perfect sphere, as when you add pressure in and there's weight, it causes the balloon to act more of an oval, and therefore a different measurement for the area and the volume of the balloon. Next, the syringe usage. We would recommend measuring the volume directly due to the error from the large imprecise units, and then the reported usage as small enough to be significant. Next, we talked about the ideal gas law. So we assume the ideal gas law can be applied for this experiment, and it should account for volume input affecting the speed of the molecule, therefore the temperature of the system inside the balloon. And then we also talked about the area assumption, because the reported views the cross-sectional area as negligible and then constant, but I disagreed, therefore reviewed on that.
Okay, time's up. Questions on the reviewer?
I'm the reviewer from TYPT, and I would like to ask some questions for both reporter and opponent. So my first question is, how do you think the pressure inside the balloon will change when you inflate it?
Like we change the amount of, so you know.
I mean, like, how do you think the pressure will increase or decrease or in other way?
I think it will stable.
It will be stable.
I believe the pressure follows an adiabatic system, which then exchange heat with the surrounding and therefore settle back to constant.
So it will increase and then settle back to the constant. Okay. So and then my next question is, how do you think the temperature inside the balloon will change when you inflate the balloon?
I think because it's
Increase or decrease or
I think it won't change.
it won't change.
I think it will increase due to the number of molecules increasing.
Okay, so then my next question is, what role does the net play in this phenomenon?
The net is like a muscle.
Is there a muscle?
Yes, the net acts like a muscle.
Okay, and then my next question is, can you tell me the similarity between air muscle and a real muscle that will cause the movement?
Like from the real muscle, the muscle triggers the movement when it acts.
So what is the similarity?
It's as similar as the tension and the change of the length.
The tension and change of the length. Okay, what about the opponent? My question is, what similarity between air muscle and real muscle that will cause the movement?
I think the force acted on the muscle is similar, however, this definitely does not encapsulate the actual muscle.
Okay, and my next question is, what do you think is the impact of different size of the balloon to the data?
I think if the balloon is bigger, I think the change might be more.
So do you think if the balloon gets bigger, will the data gets?
That's one of those obvious.
Okay, for you?
Do you mean as the balloon size?
Yeah, what do you think the balloon size will change on the data? How do you think the data will change based on different
So
balloon
if you
size?
have a greater balloon size, the pressure needed to expand it will increase, but it will still plateau and have a constant pressure estimate.
Okay, thank you. And then the next question is, what do you think is the main reason that causes the object to move upward?
I think there's the tension and the change of the length of the cylindrical.
The change of the length.
The length of the cylindrical.
Okay, so what about you?
So same as first, as you put pressure in, the volume increases, therefore losing the pulse.
Okay, that's all my question. Thank you. Hello everyone, I'm the reviewer from TYPT. My name is stage3, and now I'm going to review problem number 2, air muscle. And this is the problem statement. In my overall report later, I will be mainly focused on the main properties of muscle and the impact of elasticity of balloon and the net to experimental results. First, the overview of the report. In the theoretical model part, she talk about the force versus the elongation relationship, and she also talk about ideal gas equation. Her process should identify the relationship between tension and pressure. However, she didn't really measure the pressure inside the balloon to prove the equation is suitable in this situation. In her experiment is set up to use weight of the object, initial pressure, and the weight to press. Her process has a nice method to pump the air into the balloon. However, she didn't explain the experiment setup and the process really clearly, so we cannot really understand it. And for data analysis, she put pressure in the balloon, the push force, and the length of the theoretical net. And her process, she has compared theoretical and experimental data. However, she lacked of error bar, and she didn't mention the temperature in the balloon. I think this is really important in this question. And she also didn't mention the connection between air muscle and real muscle. Then, it's the overview of the opposition. In the short question and speech time, she talked about the independent variable, and she also clarified the elastic tension. Her process, she has clarified the way how they arrange their experiment, and they have also clarified the thing that I never really talked about, like how is their independent variable. However, I don't think she has enough question because there's still plenty of time after she finished her question. In the discussion time, they talk about ideal gas equation, pressure in the balloon, and the method to conduct the experiment. Her process, she has clarified the experiment process. However, she didn't mention the relationship between net and the balloon. And also, she didn't compare the real muscle and air muscle. And then for key discussion, first, the opponent asks, does ideal gas equation fit this phenomenon? The reporter say she agrees with the opponent that there might be another factor that will make this equation won't fit this phenomenon well. And as a reviewer, I agree with both the opponent and the reporter, and there should be another formula to modify ideal gas equation to make it fit. And then the opponent asks, when will the cross area change during the inflection, so the pressure will also change? And the reporter say it can only be suitable with a theoretical model. However, I don't think this equation of the pressure calculation can fit this situation. I think it is really weird, and I think that the pressure inside the balloon will decrease and increase. And in my question, first I asked, do both of the reporter and the opponent think that the pressure inside the balloon will continue to increase? And my answer is, as what I just said, it will decrease and increase. However, the opponent they say that it will increase and then decrease to a stable state, and then the reporter said it will be stable. And next, I asked, do you think how the temperature will change inside the balloon? The opponent said the temperature will increase, and the reporter said it won't change. However, I think that throughout the process, because continuously inflate gas into the balloon, causing the inertial energy to increase, and the temperature change is related to the inertial gas equation. And next, I asked that what does the net play? What role does the net play in this experiment? The opponent and the reporter say it is the way how it will lift the object. And then let's jump to missing points. I don't think they have mentioned elastic because she didn't really change the theoretical net, and she didn't mention the change of the length and the width. She did also mention the temperature impact in the experiments. That's all for my review. Thank you.
Concluding remarks.
So for the remarks, different variables that might affect the dependent result. In offering an qualitative explanation for the case to two varying variables. A theoretical explanation for this tautology accounts for the possible errors in experiments. Multiplication of the theory through comparison. And change by applying the ideal gas equation and real gas situation has such a small impact in room temperature that we can consider it with negligible at a fixed state of temperature. So from the formula, as the F increases, the A will increase too. Then for the discussion, the tension from the net project onto the surface A, which causes the pressure. So that's the end.
Good question of the jury. Any questions or comments?
Okay, so I have a question for the reviewer. What do you think the relationship between the pressure inside the balloon and the contract force of the net? The relationship between the pressure inside the balloon and the contract force of the net.
So I think that at first, because the balloon is still not very big, so I think the pressure of it will increase. Like as what I just said, it will every time you punch, it will like decrease first and then increase. But as it touches the net, because the net will it will control the volume of the balloon, so I think the pressure will increase more in every push of the. Okay.
Okay, the pressure inside the balloon is increasing, so the contract force of the net is increasing or decreasing or remain the same?
I think it's increasing.
It's also increasing. So what do you think for the opponent? What's the relationship between the pressure inside the balloon and the contract force of the net?
The
Contract force.
I think
Contraction force.
I think
Contraction.
it will also increase because as you have more pressure, there's more.
They are proportional. Okay. So what do you think?
I think when
The
the
reporter.
pressure is not changed, the force will increase and the area will decrease.
Thank you.
Any more questions? No? Please be curious.
Okay. Thank you.
Okay, let's
Reporter.
now the score for the reporter.
Okay.
56666. 7.
Consistent.
Okay, thank you for everyone's participation. You are doing a very good job.
Yeah, have a nice evening.
Yeah, have a nice evening. And good luck.